Thanks for viewing this short summary of the paper, Learning Insulin-Glucose Dynamics in the Wild. This work was done with Nicholas Foti and Emily Fox. Type 1 diabetes, or T1D, is a chronic condition in which little to no insulin is produced, frustrating the regulation of blood glucose. T1D requires constant management, monitoring glucose levels, meticulously tracking meals, tuning insulin delivery, and planning physical activity. Dangerously low glucose levels can lead to loss of consciousness or death. Chronically elevated glucose can lead to kidney, cardiovascular, eye, or nerve disease. Forecasts of blood glucose can play a role in the management of T1D. Here, we focus on a model-based approach to generate glucose forecasts using data recorded by a continuous glucose monitor, also called a CGM, an insulin pump, diet logs, and activity measurements. Our objective is to model the dynamics of insulin, glucose, and carbohydrates for real-world T1D data. Existing approaches for forecasting blood glucose broadly fall into two categories: statistical and physiological. Statistical approaches, like the classic ARMA time series models, or machine learning models, like RNNs, find patterns in the observed time sequences. No mechanistic information is specified in these models. Structure is derived purely from observational data, which can lead to physiologically implausible forecasts, like a rise in glucose following a bolus insulin dose. Alternatively, physiological models, such as the Bergman minimal model or the UVA-Padua T1D simulator, describe the dynamics of glucose, insulin, and carbohydrates in the body, often with a set of differential equations. While these models impose realistic dynamics, they can be too constrained to accurately describe real-world glucose data. We take a hybrid approach. We incorporate a physiological T1D simulator and a state space model as two components of a statistical and physiological hybrid. The UVA-Padua T1D simulator component describes the individual's physiological state, and the latent state space model allows the physiological T1D simulator parameters, such as insulin sensitivity and carbohydrate absorption rates, to fluctuate in time. We find that, while the static T1D simulator struggles to model real CGM data, the increased flexibility of the hybrid approach allows for a far more accurate description of CGM data. Additionally, the hybrid model inherits realistic constraints from the T1D simulator. While a purely statistical model may make physically inconsistent forecasts, such as glucose rising after a bolus insulin dose, we find that the hybrid model makes physiologically plausible forecasts in new contexts. To summarize, we show that a hybrid statistical and physiological model can enjoy the best of both worlds: the expressivity to describe real-world CGM data, and the inductive bias to generate physiologically consistent forecasts. Still, long-range blood glucose forecasting remains a challenge, and our analysis was limited to a small cohort with observational data. Larger follow-up studies will be needed to understand clinical implications. In future work, we hope to model meals, particularly missing ones, and incorporate additional physiological signals into the algorithm. Thanks for listening.